For part 1 of the exponent laws video, I will review the 7 main exponent laws, and then if you want to continue to part 2, you can see some examples of how they are applied with each other and, of course, in more detail. The first exponent law is when we multiply numbers with the same base. The law says that we keep the same base and we add the indices. And of course, indices is another word for exponent. Let's look at why this is true. If I have 7 to the power of 4, that's 7 times 7 times 7 times 7. 7 to the power of 2 is 7 times 7. So if I multiply all of that together, I in essence have 6 7s being multiplied, or 7 to the power of 6. The shortcut is by realizing that if we add the original two exponents, 4 and 2, we get 6. That's why this holds true. So if we have x to the power of 6 times x to the power of 7, we can simply add those exponents together and get x to the power of 13. In the same way, if we divide numbers of the same base, we can subtract those exponents, or indices. Let's see why that's true. If I have y to the 7th, that means y is being multiplied by itself 7 times, and y to the 3rd means y is being multiplied by itself 3 times. So if we look here, we have 7 y's on top, 3 on the bottom. These would cancel, these would cancel, these would cancel, and I would be left with just these 4 y's, or y to the 4th. Therefore, if we realize that by subtracting the exponents we get the same answer, we can save a lot of time. So let's look at another example. Here I have b raised to an exponent that is a variable divided by b to the 2nd power. Well, let's do the same exact thing. Let's just subtract exponents. The only thing with this example is that we cannot simplify any further than b to the power of x minus 2. But if x were to be substituted by any value, we could subtract and simplify. The third exponent law has to do with a power raised to then another power. The first example, a to the power of 2 raised to the power of 4. Well, let's break this one down. A to the power of 2 to the 4 means a to the 2 times a to the 2 times a to the 2 times a to the 2. Well, by using the first exponent law, we're multiplying like bases, we can simply add those exponents together. 2 plus 2 plus 2 plus 2 is 8. So looking at the law, it's like a shortcut. If we have a power raised to a power, then we multiply those two exponents. 2 times 4 gives us 8. So in this example, if I have x to the power of 6, then raised to the power of c, then that means I would multiply those exponents and get x to the power of 6c, because 6 times c we write as 6c. The fourth law has to do when you have a product that is raised to an exponent. Let's look at this example to understand why it works. 3x to the power of 4 is 3x times 3x times 3x times 3x. So in essence, we have 3 raised to the power of 4 and x raised to the power of 4. 3 times 3 times 3 times 3 is 81, and then x to the power of 4. So the shortcut is we could raise each of these to the power of 4. 3 to the power of 4 times x to the power of 4, and we would get the same final answer. So let's look at another example. In this example, we have 3 things inside the parentheses, all being raised to the power of 5. So we have negative 2 to the power of 5, a to the 3rd to the power of 5, and then b to the power of 5. So let's simplify. Negative 2 to the power of 5, that's going to be 5 negative, so it stays negative 32. A to the power of 3 to the power of 5. We multiply an exponent raised to an exponent, so we get a to the 15. And then our last term is, of course, b to the 5th. This middle step we could cancel. We can go straight from the first to the final answer if you can see how to do that. If not, writing that middle step will always help you to avoid errors. The fifth rule is very similar to the fourth. It just has to do with a quotient, or a fraction. If you have a quotient, all raised to a power, again, then that power goes to everything inside that quotient. So we could rewrite this as 4 to the power of 3 over z to the power of 3. That exponent goes to the numerator and the denominator. Well, let's simplify this further. 4 to the power of 3 is 64, so we have 64 over z to the power of 3. One more example, a little more complicated. We have in the numerator a product and in the denominator a product. So it's like we're taking the last two exponent laws and we're putting them together. So we're going to raise everything inside this to that power. So we have 7 to the power of 2. A to the 5th to the power of 2. Well, we multiply exponents being raised to an exponent. So that's a to the 10th over b squared, c to the 3rd to the 2nd power. We multiply those exponents. We get c to the 6th. And again, one last step. I'm going to simplify 7 to the power of 2 to get 49. So 49 a to the 10th over b squared c to the 6th. Now the next exponent law is one of the more simple ones. It just says any non-zero number raised to the power of 0 is 1. So here, what is 24 to the power of 0? 1. What is 5 to the 0? 1. Plus 5 squared, we know is 25, so we get 26. And this last example, anything raised to the power of 0 is 1, but this negative is not inside the parentheses. So we have negative, and then 7y to the 0 becomes 1. So the important thing to realize here is that the final answer remains negative, because the negative is not being raised to the power of 0. Now the last exponent law has to do with negative exponents. In mathematics, we don't like negative exponents. We want to figure out a way to simplify them. Well, if you look at this law, it says that anytime you have a negative exponent, if we move that value down to the denominator and make the exponent positive, then we have the same relationship. In the same way, if the number is already in the denominator, raised to a negative power, we can bring it up to the numerator and make it positive. And of course, we have this simple example here of a to the negative 1. Means we can move the a to the denominator and make it to the power of positive 1. Well, let's look at some examples to make that more clear. Here we have x to the power of negative 2. If I want to make that exponent positive, since we don't like negative exponents, I would move this to the denominator. So I would have my final answer with a 1 over x to the power of positive 2. So all we've done is we've taken this value, moved it to the denominator, and made the exponent positive. Let's look at an example that may make that a little more clear. In this, we have the same base, x, in the numerator and the denominator. And our properties said that when we divide like bases, we subtract exponents. So if we subtract 3 minus 5, what do we get? We get negative 2. Well, this is the same thing that we had in example A. Let's write this another way. If I had x times x times x over x times x times x times x times x, so 3 x's in the numerator, 5 in the denominator, it looks like 3 of these x's in the denominator would cancel, and I would be left with 2 x's in the denominator, or 1 over x squared. So this is another way that shows us that x to the power of negative 2 is the same thing as 1 over x to the power of positive 2. And when there's a final example, we have something in the numerator raised to a negative power, so we're going to move it to the denominator and make that exponent positive, and something already in the denominator with a negative exponent, so we're going to move it up to the numerator. So we're going to have x to the power of positive 4 in the numerator, and 5 to the power of positive 1 in the denominator. And remember that anytime you raise something to the power of 1, we don't write that. We just leave it like 5.